Okay, three situations. One is fully immersed, another one is partially immersed, another one is immersed in air. All three cases, we have buoyant force. How do you calculate buoyant force? F equal rho v g. How many types of forces are there so far? You have learned from your chapter 2. F等于 ma mg f d r. Okay. Net force, weight, friction, tension, reaction. 这个是 due to surface 啊，你有 surface 你就有 reaction. And then you add one more here is your buoyant force, your upthrust. Okay, so what is upthrust again? If you put an object inside a liquid or you put it inside air, then you will have upthrust. So we know upthrust is acting on the object here, staying here, and also here. Where does this upthrust come from? It comes from you displacing the air. Okay, by putting the object in the liquid, you're displacing the liquid. Putting the object in air, you're displacing the air. So that gives you the upthrust force. How do you calculate upthrust force? F equals to rho Vg. Again, I want to highlight this one. Whose density? Density of the liquid. Density of the liquid. Density of the surrounding air. Whose volume is this one? That is the volume displaced. So first situation is the total volume of the block. This one is the volume that is submerged. And for the balloon, it's completely in air, right? So the total volume here is the volume submerged. Right? So this is the volume submerged in air or in liquid. Then this is your gravitational strength. Now, 如果你看这个 formula, density 乘以 volume. Density for liquid 的话 density of liquid 乘以 volume of liquid being displaced. What is density times volume? Density 等于 mass 除以 volume. Density 乘 volume 等于 mass. So, liquid, mass of liquid. Right. That means this one you can also write it as buoyant force equals to mass of liquid times g. So what's the mass of liquid times g? That is weight of liquid. This one is weight of liquid displaced. Weight of liquid, or I say air being displaced. You take this volume, the weight is the buoyant force. You take this volume, the weight is the buoyant force. Same, you take this volume of air missing, the weight is the buoyant force. Now remember, inside the balloon you got helium gas or hydrogen, whatever, other than air. Not the weight of the helium inside, is weight of the air that is being displaced, is the surrounding air outside. Okay, you got two types, air, atmosphere, and then inside you get another gas. Okay, it can be helium, hydrogen gas, any gas. The buoyant force, how do you calculate it? It is the weight of the atmospheric air being displaced, not the helium air inside. Okay, so we arrive to this one is your Archimedes, right? Archimedes says buoyant force is weight of liquid. Now, 他只是跟你讲怎样算 buoyant force， 他没有跟你讲 object float 还是 sinking, right? It just this part is just telling you how to calculate only, how to calculate your buoyant force. If I want to see whether the object float or sink, then I need to compare the buoyant force with other type of forces, because you learn about equilibrium in your chapter 2. How do I make this thing floating? You must make it equilibrium. How do you make it equilibrium? What are the other forces that could be acting on this object? Is there MA? There's no acceleration. Is there mg? That's the weight of the object. Yes. Here, W equals to mg. You have mg here. You have mg here, and you have mg here. So we have this. Do we have friction? Object is not moving here. We will neglect all friction. We have tension. We do not have strain. No tension. Reaction. There's no surface. And then updraft also already. Here. Okay. All the forces I labeled already. Is it a balance force? So if this is a balance force, then this object will be floating. Okay. So 这一 part 跟你讲 buoyant force 讲酸，可是它 float 还是 sinking? We have to compare with the weight. If this buoyant force is greater, this thing will accelerate up. Even your net force upward. 如果你的 weight 比较大 then it will accelerate down all the way to the bottom. Okay. Now for floating object, if you're still a bit not clear, okay, you see here for floating object that floats. Very important. What is the condition? Buoyant force, keeping out the mean, mg. Okay, this is the condition for floating. We are just talking about floating, huh? Buoyant force 等于 mg， 然后 buoyant force 也是 weight of liquid displaced. So we write weight of liquid displaced 等于 mg 是谁的 mg object 的 mg object 的 weight of object. Okay, weight of liquid displaced and weight of object. This is the condition of floating. If you want to float, you have to make sure that the weight you displace, this object displaced this much, must balance out its own weight. Say this object have to make sure if it wants to float, the weight of the water it displaces must balance with its own weight. If you jump in the water, the weight you displace, if you are completely submerged, that's the maximum weight you can displace already. Let's say you jump in water. So how much liquid you are displacing? This volume, the same as your volume, the volume of your body, right? This volume of water is being displaced. If you go and measure that weight, does not equal to your own weight, then you will not float. You will sink. Again, what is the condition? You have to make sure the weight that you displace must be balanced by your own weight. I'll give you another example. Okay, let's say this is the container ship. The mass of, let's say, okay, 50,000 tons. If the ship wants to float, then it has to make sure what? The weight it displays, this volume. If you take this volume of water, go and measure the weight, this must be equals to 50,000 tons. If not enough, then you have to go deeper. If not enough, then you have to sink. You have to sink deeper. Because sinking deeper, you display more and more liquid, right? So you keep sinking deeper and deeper until you display the same amount of weight as the container ship. Right? This is why one of the reasons of why when the ship goes to the river water. This is seawater. Seawater, you know, is higher density. Okay, because seawater has a lot of salt in it, right? So a lot of salt contain a lot of impurities, particles inside. So the density overall is going to be heavier. It's going to be heavier. Just imagine if you have two water compare this one. This water, you add a lot of sugar, you add a lot of salt. Okay, for the same volume. This one you add so many particles inside. This one will be heavier. This one is lighter. So generally, seawater, the one with the more salt in it, will be higher density. Okay, because there's more particles inside. Same volume, but more mass. So this is higher density. Then, if you compare it to fresh water, river water, lower density. So when the ship goes to this water, how? Now it goes to this water. 因为这个水 lower density 对吗？那记得我们要 displace， 我们 displace 的 liquid 啊，重量一定要跟我们的重量一样。所以如果我的水是 lower density 的话 ，then it means I need to displace a lot more, right? A lot more to balance my own weight. So that means if you compare higher density liquid and lower density liquid, you see that the ship sink more water must be displaced because liquid is less heavy. It's less heavy. Higher density water, they are more heavy. So you don't need that much water. This one, you need to sink more to displace more water because the liquid is lighter to balance your own weight. So as the ship goes from seawater to river water or higher density water to lower density, then you will see it sink more. Okay, more and more liquid will displace. And the same is true in other way. As you go from lower back to the higher density, you only need to displace a little bit because the water is very heavy already. Higher density. So this principle, they used to make a device. They used to make a device like this. They put a tube on, and then they put particle here. It can be any particle, sand as you can, just to keep it vertical when you put it inside water. Now let's say you put this thing inside water and then it floats. Water having density of 1.0 gram per cm cube. Okay, EgCm cube is 1000 kg per meter cube. Now let's say you make a device like this, and then you put sand just to make it put some weight here just to make it vertical, so as it floats, it remains vertical. Then you see it floats. Water level is over here. Then I will make a marking. Here, I make a marking 1.0. And then I take out, put it in a liquid of higher density. Let's say this one liquid X having density of 1.1. Higher density. Okay, this is my marking. Now, what is the position of the device? I put it in a liquid of higher density. So again, higher density. 如果在这里的时候，你 display 多少 liquid? This much of liquid you display. This volume underwater, right? So you display this much. If you put in the higher density liquid, the liquid is heavier, right? So you don't need to displace that many You only display, less than that one. So what happens is this one will rise up. This one will rise up, and then this is the marking 1.0. Then we make another marking for this one. Here is 1.1, higher density. Okay, so how much volume you display? This much. Now I take it out again, I put it in the third liquid, having density of 0.9. What will be the position of the device? 0.9 is less than this one. So that means if this one displays this much, then this one has to display more than that one, more than the first one. So as a result, this one go deeper. Very slow. One, and then here we make a marking. This is 0.9. Okay. So overall, if you put it in a denser liquid, it rises up. If you put it in a less dense liquid, it goes lower. What is the reference? The reference is water. So you start at water, reference point 1.0. If you put it in a density higher than water, it rise up. Lower, then it goes. So this device, we take it, we make it a lot of marking, starting from 1.0. Then you know this is water density. If you put it in an unknown liquid, you want to measure the density. It shows at this level, then you know it's the same density as water. If it's below this, then you know it must be denser than water already. Right. So that's why 1.0, the reading increases downward. 1.1, 1.2, 1.3, and decreases upward. 0.9, 0.8, 0.6. Okay. This is used to measure liquid density. They have all the reading already. The reading should increase downward because we know as density of liquid increases, it rises. So the reading should increase downward. Such device is called a hydrometer. Okay. It works based on the same principle as okay, you can do the exercise. If you finish, you can submit. This is the first question. Find the mass of the balloon. Okay. Mass equal to density volume. So you got the density and the volume of the block. The volume is the total volume, not the volume of submerged. This is the volume of the block. So 800 times 0.6. We got 480 kg. B. Find the mass of the displaced liquid. Displaced liquid is the block floating. You have to see first, is the block floating? Okay, yes, it is floating. So if it's floating, means what? If it's floating, meaning that the weight of object 等于刚才我们的 condition 是什么 ？weight of object 一定要等于 weight of liquid displaced. Okay, so if it's floating, then the weight of this object must equal to the weight of liquid displaced, and they ask to find the mass of displaced liquid. So 我们写出来 weight of object 等于 weight of liquid displaced. Weight 是等于 W 等于 mg. Mass of object 乘以 G 等于 mass of liquid 乘以 G cross product mass of object 等于 mass of liquid displaced. Okay, so answer is also 480. All right, back to this one. We said if you want to float, what happens? You must display the same amount of weight as your own weight. So if this object wants to float, anything else displayed, 这样子的 liquid, 这一 portion, this portion of the liquid must be the same weight as the object weight. Right, so that's why, okay, we got this one, 480. Okay, right? Now, see, Find the volume of the wooden block that appears above the surface of the liquid. 给条你找这里的 volume that comes out from the surface. We got the total volume 0.6. Can you find the volume submerged? Find volume submerged. Volume submerged. Okay, from the formula of F, V, rho, V, G, the buoyant force, the formula. What is my buoyant force? Buoyant force is the weight of liquid displaced. So 480 kg times 10 is your buoyant force. Right, so report back. I just now wrote it on now this one. If you from here just now, force equals to mg. Buoyant force, the mean weight of liquid or air being displaced. Because the part some okay, G rho V this one I can cross. Whose density is this one? Liquid density. 1200. Okay. Volume submerged 0.4. Okay. Volume above water surface. Link点分。 Number 5, okay? Yes. For question 5. Okay, volume water displaced. Now, take the area, cross section. Cross section area is this is your test tube. Cross section is this one. You take this area, your cross section area, then you times by the length. You get the volume of water displaced. A2, weight of water displaced. Now you have the volume of water displaced, get mass first. Mass equals to density into volume. Density of water, 1 gram slash cm cube times into 18 gram. Weight. B1, write an equation to relate the forces. Okay, B number 2, calculate the mass of sand in the glass tube. mass of sand in the glass tube. Okay, this is your mass of your glass tube is 12 gram. Mass of the sand M, and then mass of the liquid being displaced. So this is time it up. A2 mass of water displaced 8 gram. 总共的 mass 12加 sand 的 mass 一定要等于你 displaced liquid 的 mass. Okay, so your displaced liquid mass 18 gram, the tube is 12, this one must be 6. 6. Right. Yeah, it's the same principle. The weight of the thing, same as the weight of the liquid. The mass of the thing, same as the mass of the liquid. Right? Because weight and mass, same thing. Just times G, you get weight already. Total mass. Total mass to total weight. Okay, C. The glass tube is later placed in a beaker containing alcohol, lesser density. State the change to the section of the glass tube immersed. Okay, you place it in alcohol, which has lesser density. So again, less density, they are lighter liquid. You need more liquid to balance the weight. So it will sink deeper. And if it sink deeper, this L will increase. Explain your answer. Because alcohol has lower density. What is the application? Hydro. 给英题。A balloon filled with gas X at volume 0.2. The balloon is stationary. When a load is hung to it as shown in the figure, given that the total mass of the load and gas X is 0.2, Okay, total mass gas 加 object 0.2 kg, and the mass and the volume of the balloon can be neglected. Okay, what is the total weight of load and gas X? The total mass you have already, you just change it 0.2 kg times 10⁵ Newton. B, what is the upthrust of the balloon? Upthrust. Okay, the balloon, is it floating? It says in the question, the balloon is stationary. Stationary. That means no acceleration. So your upthrust force is balanced out by the weight. So what is the upthrust? Same as the weight. Also 2 Newton. See, what is the weight of the air displaced by the balloon? Weight of the air displaced by the balloon. That is also asking for the upthrust. So upthrust is the same as the weight of the displaced liquid, right? So in this case, air upthrust is same as the weight of displaced fluid. Same as weight of displaced fluid. That is also 2 Newton. Same 2 Newton, 2 Newton, 2 Newton. D, what is the principle? Okay, Archimedes. And E, what is the density of air being displaced? Density of air being displaced. Okay, what formula? Density of air being displaced. 如果我要找 density air being displaced, the atmospheric air, not the gas X. So first I need to know what is the volume. What is the volume displaced? From this, F equals to rho dg. Okay, neither buoyant force to density of the air. Oh, sorry, they want to find density. So density, then volume is 0.2. 0.2 times into 10. Okay, last one. When a string 1.0 kg/m, and then okay, right? 你看 F when the string attached to the load snaps, the balloon will accelerate upward with an acceleration of 1. Calculate the density of gas X. When the string snaps, so that means, let me sketch the force diagram. So when the string snaps, the weight gone. Now, what is the forces acting on the balloon? We have upthrust, and then you have also mg. So the mg now changed already because no more the weight. This is the mg on the gas X. And then it says this thing accelerates upward with an acceleration of 1 meter per second squared. If it has acceleration, so the force is not balanced. This one and this one. Is this case floating? It's not floating already. Floating is stationary. This one is rising. right? Rising means you have net force, you have acceleration. In this case, initial case is floating, stationary. But this one, you have acceleration. So you can apply F equal ma. Force 是你的 net force. Okay, net force 是 U minus mg 等于 ma. Then U is 2 Newton minus the mass of the gas, mx, times by 10 等于 mass of the gas times by 1. 2 minus 10 mx equals to mx. 2 equals to 11 mx. 2 divided by 11. So your mass is 0.18 kilogram. Density mass divided by volume. So density of x, mass x, volume x. 0.18除以0.2 0.9 kg/. Question 7, last one. A ping pong ball of mass 10 gram and volume 20 cm is immersed completely in water. Density given. When ping pong ball is released underwater, it floats to the surface. When the ping pong ball is released, it floats to the surface. So we have rising means buoyant force is greater than mg. That is your 7a. 7a. Why does ping pong ball float to the water surface? Upthrust bigger than mg. So you have acceleration. You have acceleration because this one bigger than this one. You have net force. You have a certain acceleration. Now, B, what is the upthrust acting on the ping pong ball? Okay. Force equals to rho V G. Density of water 1000 times by volume submerged. Now be careful here, this one is kg/m3. This one is 20 cm. You have to change it. Okay, cn cube 到 m cube 啊，除以1 million 对吗？20乘10减6，对，除以1 million，除130次，对，除100，除100，除100，所以是除1 million，then times 10，0.20。C minutes. Last one. Calculate the resultant force acting on ping pong ball. Resultant force. Okay, so we have up thrust. You get the mg. Mg equals to mass of the ping pong ball. You have the mass ready on 10 grams. Okay, 10 grams 除1000乘10.1 Newton. Resultant force to be Newton. Then in Newton. That is your resultant force. And if they ask you for acceleration, then you can use that to get acceleration.